Good evening, dear participant, and welcome back to this 10 days workshop on biostatic from basic to advanced techniques. Today, the session will be on probability fundamentals, and resource person will be Dr. Prayas Sharma, Department of Statistics, Babasaheb Bhimrao, Ambedkar University, Central University, Lucknow, India. Before inviting today's resource person, I would like to have a brief introduction about our eminent resource person. Dr. Prayas Sharma is currently working as assistant professor in the Department of Statistics, Babasaheb Bhimrao, Ambedkar University, Lucknow. Dr. Sharma holds a bachelor's degree in computer science and statistics, master and doctorate degree in statistics from the Banaras Hindu University, Varanasi, India. He has qualified national eligibility test and obtained the junior and senior research fellowship from UGC India. Dr. Sharma is certified virtual teacher by University of California, Irvine. Dr. Sharma has good knowledge of statistics, artificial intelligence and machine learning, business analytics and research methodology, along with a strong computational and programming skill. He has more than 10 years of academic experience, both in domain of teaching and research. He has worked earlier with reputed institute university like Indian Institute of Management, Sirmur Ghati Shakti University, Vadodara, and the University of Petroleum and Energy Studies, Dehradun. His research interest includes survey sampling, estimation procedure, using auxiliary information and measurement error, predictive modeling, business analytics, operation research. Dr. Sharma has published more than 45 research papers in the reputed national and international journals, along with one book and two chapters in a book internationally published. He has more than 580 citations with the H index 17 and I index is 20. So today's resource person has vast experience in this domain, and I hope that his expertise will be very informative, knowledgeable to all the participants. Welcome, Dr. Prayas Sharma, in this session. Over to you now.
Thank you, sir. Thank you for such a detailed introductions of mine. Indeed, the pleasure is mine, and I would like to thank you that you have given me the opportunity to interact with the learned mind. And I personally enjoy, interacting with those and sharing the thoughts with each other, and that's how we build up the relations, we build up the concepts in academics, right? And I would also like to congratulate you to suggested such a nice topic of the workshop and such a fruitful workshop for the participant. I'm sure that the topic which you have chosen and how you have designed the whole workshop will be many beneficial for the participants. Okay, so now shall I share my PPT?
Yes, sir. Please.
Right. Hope this is visible.
Fine, sir.
Great. Thank you. Thank you. So, good evening, everyone. You already have gone through my, about my past and present in terms of academics, research, etc. And then we'll now start discussing about the concept related to the statistics, particularly in the probability and probability distribution today. At any point of time, whenever you feel asking any kind of questions, feel free, right? You can write in a chat box, you may raise your hand, you may just stop me and ask the questions, right? In fact, I personally believe that interactions is much better than while the one way listening or one way communicating to the students. And I also would like to learn from your expertise, learn from your because we are in a different sector of the world. So definitely we would learn from each other, and definitely I would like to learn from you. So please feel free at any point of time wherever you feel asking, or if you would like to add something to the contents, so that we can work on that. Uh, when we talk about the probability, very basic things comes up that we have to go in our day-to-day life. That is the randomness, right? And randomness and the uncertainty. So everyone, every common people, every layman would take many kinds of decision into his day-to-day life, right? Such decisions may be whether I should, go with a car or not because it's a rainy season, whether I should take certain decisions or not, whether or what are the chances that the sale will increase of the prices, what are the different likelihoods that a new assembly methods will increase productivity, what are the chances that certain product would be having less price in the coming sales, right? And that's how we decide, you know to take the decisions on that. And such environment is purely random, purely uncertain, right? So the concept is of the probability. If we can have certain knowledge about this uncertainty or this randomness, perhaps the quantitative knowledge of this uncertainty or the randomness, then the decision making would be better in terms of, if we take the decision without having any knowledge, without having any idea about the situation. The conceptually, this is the idea when we would like to discuss the probability. As a student, when you would take say the probability, it means it's just a numerical methods of having or getting a likelihood that an event will occur, and that event can be any event be life, right? Later on we'll see what are the basic requirements to calculate the probability into different phases, different stages, and how it can varies from our day-to-day life to a very specific random experiments. In the coming slides we'll be seeing those things. Now, as I said, so in terms of the classroom definitions, the probability is a measure of the uncertainty, or maybe the quantitative measure of the uncertainty that an event will occur. Probability lies between 0 and 1, and that's why usually we say certain things that there is a 50% chance of happening, maybe 20% chance of happening, 60% chance of not happening, etc., etc., right? Now, there are three methods of understanding or getting the probabilities. One is the classical method of assigning the probabilities, where we have certain rules and laws, right, which will be seen in the coming slides. Another one is the relative frequency of occurrence, right, where we have the past data, and based on the past data we would like to calculate the relative frequency, which is can be seen in terms of the probability, the chances what will be occur, right? So for example, that if you say that 50 students have applied to these posts in the last 10 years, and out of 50 only 5 of them are getting selected, right? So what is the probability that a person will apply for this job or test, this getting selected? You can get the relative frequency, and that will certainly be like a probability. Next is the subjective probability, right? Subjective probability is the probability which is totally based on the personal intuitions, the experience, the reasoning in this field. Definitely, the person who is working in the field of, you know, uh, every day in the field of any industry, let's say in the share market, right? And a person who is not very much interested or very much expertise in the share market, then their probability of getting a stock going up or going down, they both can tell you the probability, but certainly the probability would be much better than the person who is not expertise than the person who is expertise into that area, maybe belonging to the stock markets, right? So these are the three different kinds of probability. So we'll discuss one by one and we'll see how it varies and how what are the differences on them. So classical probability is a very simple one. That's number of favorable outcomes divided by total number of outcomes. That comes in the classical level of the probability, and this is and each outcome should be equally likely, right? And this is also applicable to the game of chances wherever it is required. The objective in such probability definition is that everyone, means every participant or every kind of thing having the same and identical probability assigned to them, and therefore you can get the probabilities as equal, right? Otherwise, just to have a concept of that, if you would like to calculate the classical probability, that would be the number of favorable number of outcomes divided by total number of outcomes. Favorable number of outcomes means in which you are interested. It's nothing related to the favorable to the situation in which you are, right? It's only related to what is your objective of getting the things done, right? That would be called as a favorable. Next is the empirical probability, as I said, relative frequency probability. So whenever the data is being given, we can calculate the relative frequencies, and that is the probability, right? We'll see in the future slides whenever we'll be having these examples. Next is the subjective probability. And as I said earlier, that the subjective probability is probability which is based on the intuitions, reasoning, and more important, that experience of that person, right? Many a times people say it's an intuition. It's not really the intuition, rather it's the experience into that domain, into that field, right? And definitely that that experience is much better useful to express the probability in terms of something, in case of the uncertainty. And since it's a subjective, because why we are calling it subjective, because it varies from person to person, because different individuals may be having the different experience into that domain, that case of knowledge. Still, if they have the same number of experience, their logical reasoning, their behaving of seeing the things would be different, and therefore the probability would be different. That's what we call it as subjective, right? Such kind of probability is very useful in the field of management, right? Specifically whenever you are going to launch some new product, you are going to see some site selections from some site selection from for certain constructions, right? For some sporting events, etc. So these are much beneficial at that case. Now, if you talk about the basic structure of the probability, right? Now we are talking about the classical probability, keep in mind. So we have, these are the nomenclature which will be useful later on. That's experiment. An experiment is what? The process of producing an outcome. So if we say we toss a coin, right? And if we toss a coin, how many heads and how many tails are there? That is called the experiment. Event and outcome of an experiment, that will be called as an event, right? Elementary event that cannot be decomposed or that cannot be further broken into the smaller parts, that is called the elementary event. Sample space, the complete list of elementary events which we have seen in our case, the complete list of elementary events will be called as a sample space, right? Trial is one repetitions of the experiment or process. So for example, if you roll a dice once, it's one trial. If you roll a dice 10 times, it's a 10th trial, or 10th trial of the 10 times. Some another nomenclature to understand the probability deeper would be mutually exclusive event. such event that the occurrence of one precludes the occurrence of the other. That means one doesn't one event doesn't allow to exist the another one, right? And therefore these events do not have any intersection points. For example, if you toss a coin, then head and tail are the mutually exclusive event. There cannot be any intersection, and if head comes, tail cannot come, and vice versa. Independent event, the when we say the two events are independent, when the occurrence or non-occurrence of any one event has no effect on the another one, then two events would be independent event. Collectively exhaustive event, which is list of again all possible elementary events for an experiment. Complementary events are two events, one of which comprises all the elementary events of an experiment that are not in the other events, right? That would be called the environments. Next is the sample space. So we have seen earlier the sample space is the list of all the elementary on an experiment. For example, if you are uh, 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 predicting predicting or showing the sample space, one is roster or listing T diagrams.
Sir, your mic is not stable.
Yeah, just to make you make the more understand form, these are the different ways of showing the sample space or list of all possible events. You can see with the help of this example, right? So experiments will be randomly select without replacement two families from the residents of that any town, and each ordered pair that shows here in the right hand side, right, will be then elementary events. So for example, if we have to select the sample of size 2, we have selected AB, maybe AC or AD and so on, right? Where A, B, C, D are the family names. They have the different children in the households, their number of automobiles, etc. We also denote this sample space in the form of the set, as I said. So set, and then inside the set we have x, y, where x is the family selected the first draw and y is the family selected on the second draw, right? Now we'll see some parts of the sets and their union intersection, which will help us to understand the different laws of the probability. So, if you say we have suppose the two sets, let x and y, and x is having the elements say 1, 4, 7, 9, and y is having the elements 2, 3, 4, 5, 6. Then we can have the union of this set. Union of means which is having in a set A or set B. That is the definition of the union. So we write x union y means the elements which is set x or the elements which is set y. So you can see now it would be 1, 2, 3, 4, 5, 6, 7, and 9, because you can see that 2, 3, 4, 5, 6 is in y, and we have x 1, 4, 7, 9. Now we have written the union, and you would notice that there is one point is common, which is 4, but we don't have to write it twice because it has included, right? And what does it mean? It means that the properties of that element has already included in this sets. Therefore, it's not required to write it twice, right? But when you see this Venn diagram, there's X and there is Y, and you can see there is a overlapping or intersection, and that intersection is nothing but an element denoting as 4. Similarly, the another example is in front of you, that is C, which is a set of few names, that is set of new, maybe you may say the companies IBM, DEC, and Apple, and F is again apple, grape, and lime, right? So C and F would be IBM, DEC, apple, grape, and lime. Clear? Any question? Fine. Next is the intersection of the sets. So you must have understood by now that we have initially the two sets X and Y. Union means which is present in the set X or set Y, whereas the intersection means which is present in the set X and set Y, right? So there we were using the word or, here we are using the word and, right? So if you can see that if we write X intersection Y, it is only the 4, right? So that set only contains one event, that is 4. And similarly, you can see here in the Venn diagram as well. In the same example, if we could find C intersection F, that is again the apple, because apple is the common into both. That is the meaning of the intersection of two sets, right? And by definition, it says that the elements which is present in set X as well as the element which is present in set Y, right? Now, when we saw the mutually exclusive events, we have seen already the definition of this mutually exclusive events, and it has that no common outcomes, right? So if you see X179, Y2345 6, and if we have to find X intersection Y, then there is no event, right? It's phi in terms of the set theory, it's phi, the null event, right? Another C intersection F, again there is no common event, so intersection would be 0. The probability of the intersection of X and Y would be 0. The same you can see and understand with the help of this Venn diagram. Independent events, we have already seen that there are independent events which does not affect the occurrence or non-occurrence of the another event. So if you have the two event X and Y, it means that the occurrence of X have no effect on the occurrence or non-occurrence of the Y and vice versa. In this case, if you would like to get the conditional probability, right? For example, probability of X given Y, which it will be certainly equal to probability of X, and similarly probability of Y given X would be equal to probability of Y, because the occurrence of Y, right, has no effect of occurrence of X. So therefore these two are independent, and therefore the conditional probability will be equal to the marginal probability of X and Y into different cases. This is called the collective exhaustive events, where it contains all the elementary events of an experiment. The complementary events, we have seen that it's complementary to the event what is being occurred. So if we say A is an event, then A dash is a complementary to the event A, right? And we also know that probability of A complement plus probability of A is equal to 1, because total probability is equal to 1. Therefore, we can write probability of A complement is equal to probability of 1 minus probability of A, right? And you can see in the Venn diagram as well that if we have the set A, right, then what is the meaning of A complement, which is sometimes denoted A dash, sometimes denoted by A bar in the different notations. Uh, Now we have the counting rules of possibilities. That what are the different possibilities to get the uh, and this will be using in the calculation of the probability. One is the MN rule, which is which we'll see later on. If we have an operation can be done in M ways and the second operation can be done in N ways, then there are MN ways for the two operations to occur in an order, right? M into N ways. For example, if a cafeteria offers 5 salads, 4 meats, 8 vegetables, 3 breads, 4 dessert, and 3 drinks, a meal is 2 serving of vegetables which may be identical, right? Then how many meals are available? We can just multiply 5 into 4 into 8 into 3 into 4 into 3, right? So we have 5760 ways of serving the meals. Now we can have the different combinations that we have if we are taking the samples from the population without replacements, then we can have the NCN combination, right? That means if there are n total possible comes and we have to select a small n from there, then NCN ways are there to be selected, right? This is similarly we have the concepts of the combinations, right? If we say a tray contains 1,000 individual tax returns, if 3 returns are randomly selected without replacement from the tray, how many possible samples are there, right? Means in how many ways the 3 return can be selected out of 1,000 individual tax returns. That is NCN, which is n factorial upon small n factorial small n and factorial n minus n, right? You can solve and you can see this number, how big is the number is, right? This is the another example to make you understand how can we get the different combinations. uh, Suppose a small law firm has 16 employees and there are to be selected randomly to represent the company at the annual meeting of American Bar Association. How many different combinations of lawyers could be sent to the meeting? Again, which will be NCN 16C3, and we can have the factorial 16 upon factorial 3 into factorial 13, that is 560. So there are total 560 ways that 3 employees can be selected out of 16, right? Okay. If we talk about the probability, we have seen these probabilities earlier. So if we are only calculating the probability of an event, that is marginal probability. If we are calculating the probability of union, we say that the probability of unions. If we calculate the probability of intersection, we call it as the probability of joint. Why? If you remember, when we were taking the x intersection y, we were saying that it has to be present in x and y, right? That's why it's calling as joint probability, because and word is being used. The conditional is x occurring given y, given that y has occurred, right? That is the conditional probability. When some of the event has already taken place, then what is the probability of happening or non happening of any other event? Now we will discuss in the coming slide the general law of additions and multiplications in terms of the probability. So if we would like to get the additions of the probability, uh, it says by the law that probability of X union Y would be segregated like probability of X plus probability of Y minus probability of X intersection Y. And this can be easily verifiable, easily understandable. If you see the Venn diagram, we have X as a set and we have another set Y. And we could find that there is a intersection point between X and Y. So if we calculate this probability of X, right, please see the slide, we are calculating the probability of whole X, which is given in the blue circle. Again, when we are calculating the probability of Y, we have calculated the whole circle of this green, right, as the probability of Y. But you could understand that this circle which is common, right, which is being shaded here, has taken twice. So we have to remove that twice part, right? Otherwise, conceptually, mathematically, it will be wrong. So that's why we have just subtracted once this common part, and you know that this common part is being represented by X intersection Y, the probability of X intersection Y. So we take it further, right? Is it fine? Now, if you have to take the probability, let us consider an example, right? So this is an example in the office where the survey has been conducted, and the survey was like that people have been asked two questions, that whether the noise reduction in the office would be improving the efficiency of the employees, or or noise reduction or space. If we can give the space to the employees, then the efficiency of the employees would be increasing. So that survey has been conducted, and the result of the survey was that 70% people says that noise reduction would improve the efficiency. 67% people says that the extra space would be, uh, you know, would be would be helpful to increase the efficiency. 56% people says that both are important to increase the efficiency, right? So if you would like to know the probability of storage reduction, or noise reduction and space, then it would be denoted as probability of n union S, and which will be probability of n plus probability of S minus probability of n intersection S, right? So you can see here the required probability is 0.81. And you may understand now, it means that 80% of the people seeing this, that either the noise reduction or the space would increase the productivity, would increase the efficiency of the employees. Is that clear? Right? Again, if you could like to, if you would like to present this problem in the form of the matrix, right? So you can see that one side is the increased storage space, another side is the noise reduction. Yes, no, yes, no. You could see that both, you know, we have seen that intersection point is 0.56, that is 0.56. This one, those who are only saying yes to the noise reduction was 70%, so we've written here 0.7. Storage space was saying 67%, so we have written 0.67. Obviously, this is 0.56, so this will be 0.11, this will be 0.14, right? And since this will be 0.7, so this will be 0.30, and then consequently this will be 0.19. So we can create the matrix, right? It may be possible that you can create the matrix at the very earlier stage, and later on you can respond to the different questions of the probability. So both the methods are really good to solve any kind of problem, right? Good. Uh, this is the next question. So if a worker is randomly selected from the company described in a demonstration problem given below, what is the probability that worker is either technical or clerical, and what is the probability that worker is either a professional or a clerical, right? All of you are requested to solve this question, and please let me know your answers in the chat box. I hope you have understood the concepts of addition and multiplication law of the probability, and the same is this question is based on the same concept. Yeah, I'm waiting for your answers in the chat box. Please feel free. I just want you to solve these questions and let me know your answers. Just have a try. So Elena says tech is equal to 0.45. Uh, I believe that is the answer of the first question, right? So you are telling me the probability that a randomly selected worker is either technical or clerical. Am I right? Okay, good, good. Thank you. Thank you that you made an effort and wrote the answer. Okay, and the second one would be 0.20. Right, good. Glad to see that at least you have attempted and shared the answer. Anyone else? Okay, so Pooja has written 0.61 and 0.22. Good, thank you, Pooja. Great. Okay. Let us see the example. You could understand that the first is based on the probability of based on the law of probability of addition or multiplication? The first one is based on the probability of addition, right? So you could see that the, yeah, very correct, addition. So probability of technical union clerical, and you know that the probability of technical is total is 69 divided by 155, and probability of clerical is total 31 divided by 155. So this probability is 0.645, right? And the probability that worker is either professional or clerical, if you see here, then again it is 44, 44 upon 155, right? And then 31 upon 155. So it would be again 0.484. Clear? Is that correct? Yeah, if you'd like to share, you can tell me that where have you done the mistakes. If not, then perhaps you realize that what have you done wrong, right? Shall I move further? Yeah, so this is another way of understanding this, the same question, TC in the form of the table, and we can write here again, right? Similarly, this happens 0.48, right? Now, if I am interested to get here the probability of X intersection Y, right, which is probability of X into probability of Y given X, and similarly, we can write probability of Y into probability of X given Y, right? Now, if I'm interested to calculate the probability of M intersection S, M intersection S, then it would be probability of M is 80 upon 140, right? And probability of S given M is 0.20. You can directly put into the formula and you will get the answer, right? Okay. Law of, uh, wait a minute, just let me put this up because, yeah. The intersection of two events is called the joint probability. I told you why we call it as the joint probability. And general law of multiplication would be used to calculate or find the joint probability, right? It means that when we say the joint probability, it means that both the event X and Y will have to occur at the same time. And that's why the and words is being used for calculating the probability of togetherness. When we say probability of X given Y, it's the conditional probability, right? And it can be understood as Y has already occurred, then what is the chances of occurring of the X, right? So this we can calculate. We can have the calculations of the probability into the two way. One, either we can convert the right problem into the matrix form and then we can calculate, or we can calculate the we can, without writing the problems into mathematics form, we can calculate the another problem which we were solving, before the slide. So we have the some married staff and some of the supervisors, right? And there are few probabilities are given. In fact, there were the numbers were given, but this is not here presented the numbers rather than probabilities directly given. So the probability that a supervisor is married, right, is 0.1143, right? There is a probability of having a supervisor is 0.2143. Probability of a selected person would be a married person is 0.5714, right? And probability that a married, if we select a person, that person will be married as well as supervisor, or supervisor as well as married, this is 0.1143, right? We can see directly from here, right? Now, if you would like to say what is the probability of getting a supervisor who is already married, right? So married has already selected. Now out of this married, what is the probability of getting a supervisor? That is given 0.20. Now if you would like to calculate a probability that if you select a person that will be married as well as supervisor, so that will be probability of married into probability of selecting a supervisor who is married, and then these two probability can easily be multiplied and get the values. So you can see this from directly from the table and can tell the probability, right? Or you may also use some of the rules and laws for calculations of the probability. That was my motive to make you understand here. uh, so law of conditional probability, you know it very well, right? We were discussing it, so I'll not go into that. This is the another example, not the another one, that's the same example. We were talking about the noise reductions and the increased storage space, right? So a worker is selected randomly and asked about changes in the office design. What is the probability that a randomly selected person believes storage space would improve productivity, given that person believes noise reduction improves productivity, right? So this probability we have not calculated at that time because we have not gone through the conditional probability approach there. Now if I ask you to do so, can you calculate this probability? Yeah, can you tell me the probability quickly? No? Okay, let us see here. If you remember, Pn is 0.70 and intersection as 0.56, and we need to know now the P as given N, which is by definition P and intersection as a Pn, which is 0.80, right? So that means there is a 80% of the chance that if you select a person randomly, he would believe that storage space would improve productivity, right? Given that the person already believes that noise reduction improves productivity, right? That means there is a higher chance of a person talks about the storage space after he is being already agreed by reducing the noise reduction, right? So that means noise reduction is playing a major role in the improving the efficiency of the employees, right? Okay. So now let us come again and the independent events. So x and y are independent event, and the conditional probability is equal to the marginal probability because there's nothing like dependence on the event, right? So we could have directly write the probabilities. So I will quickly see this example. There's a graphic geographic locations and manufacturing of B and communication is C, finance is A. So what is the probability of A given G, right? So A given G, you can see that 0.33, whereas PA is equal to 0.28, right? So this shows that it's not the means PA given G, probability PA given G is not equal to the probability of A. That means it is not the independent event. These two are the dependent event. Uh, Next is the Bayes theorem. And many a times people understand that the Bayes theorem is quite a tough concept to understand, but I believe that's very easy, as well as important concept of understanding the probability, and perhaps we use these concepts into our day-to-day life. And I'll tell you with the help of an example. uh, for example, there is the concept of the Bayes theorem is what you have certain beliefs initially, right? And based on those beliefs, you try to take some decisions. And obviously, when you are trying to take some decision, there's a probability involved. In between that process, or maybe you have some new information into that, right? And then you can apply the concept of the Bayes theorems, and then your probability of decision making would be change, right? Probability of decision making would be change. I'll just give you an example. I was I used to travel from here to my hometown usually in the week, in the week or twice. And then see I book my tickets in the train, and I try to see which train suits me while going from here to my native place. And then I decide, so I book my ticket in the train which suits my time, which takes a less time as per the as per the railway timetable, right? And then my probability of going by a train A, let's suppose, is 0.9. Why? Because it suits my time, it takes the reasonable time, right, to take me through to my native place. While I was booking the ticket, some of my friend called me and says that, are you booking the ticket into that particular train, but you know that train almost get late 1 hour, right? So would you like to book the ticket? Now you see, I got some new information which was not available, that train gets delayed by 1 hour. Now if I apply this Bayes theorem, certainly my probability of choosing that train to travel is going to be decreased, right? That is the application of the Bayes theorem. And definitely all of us, at different places, at different point of time, use the concept of this Bayes theorem, right? Hope this is clear. If you have any question, then you may please ask. You through a case study that is very real example, real case study. A proposed shopping center will provide a strong competition from downtown businesses like LS Clothries. If the shopping center is built, the owner of LS Clothry feels it would be the best to relocate to the shopping center. The shopping center cannot be built unless the zoning changes is approved by the town council, and planning board must first make a recommendation for or against the zoning changes to the council, right? Could you understand the question? Yeah, I'm just coming to that point, how to calculate, Elena. Fine. Hope the question is clear. Okay. Now it is being given that let A1 denotes the town council approves the zoning changes, and A2 denotes the town council disapproves changes, right? For construction, definitely. Now, using the subjective judgments, means subjective knowledge about those approvals, let us suppose probability of A1 is zero point 0.7 and probability of A2 is zero point 0.3. Further, the planning board, next step, the planning board has recommended against the zoning changes. Okay. and let B denotes the event of a negative recommendation by the planning boards. Given that B has occurred, right? B has occurred. What does it mean? The planning board has recommended against the zoning changes. That is the meaning. Given that B has occurred, should LS Law 3 revise the probability that the town council will approve or disapprove the zoning changes? Now, one step has already been done. Planning board has not recommended. Now, does LS Law 3 should change the probability or not? Past history with the planning boards and the town council indicates that probability of B given A1 is 2, probability of B given A2 is 9. Please understand, right? Probability of B complement given A1 is 0.8 and probability of B complement given A2 is 0.1, right? I hope you understand what are these probability, right? It means earlier probability, right? A1 is town council approved the zoning changes. So town probability that probability that planning board has not recommended the zoning changes, given that A1, what is A1? Town council approves the zoning changes is 0.2. It means this is very rare, right? Very rare to contradict one parties to the another. Whereas 2 is 0.9, right? A2 is what? Town council disapproves the changes. So it means both are going in the same direction. Approval or disapproval is quite high, right? Now, let us, as I said, to understand the Bayes theorem, we can have different ways. One is the T diagram. So in the T diagram, we can write these trees, right? And finally, these outcomes. The another way of understanding this, we can write this all probabilities into this form, right? And we can calculate this one. So if you see here, given that planning board's recommendation not approves, the zoning changes will revise the prior probability as follows. Probability of A given A1 given B, you need to know. So that is probability of A1, probability of B given A1, and so on and so forth. And that has comes out to be 0.34. 0.34, right? Earlier, the probability of A1 was 0.7. Now, A1 given B is 0.34. Similarly, the planning board's recommendation is good news for LS growth. The posterior probability of the town council approving the zoning change is 0.34 compared to the prior probability of 0.70. So now the decision which was taking, right, and the probability was 0.70, after or getting a new information in between and applications of the Bayes theorem, the same probability of decision making is changed to 0.34, right? So this is called the approach of the Bayes theorem, which improves the probability. We call it as prior probability and the posterior probability for improvement of decision making as well, right? So we also have the another way of presenting these probabilities into the tabular form, right? The same approach has to be followed, and here is the uh, here is the table which shows you the things, uh, the calculations of the Bayes theorems, right? Any question? Okay. So if there's no question, then we'll probably move towards the next part of this part of this session, which is probability distributions, right? So as quickly as we have seen that probability earlier, we will see the probability and statistics, the difference, a little difference in while telling these two terms, because we cannot say these two terms interchangeably. So we'll just try to understand the difference between these two. So probability, as we said, is the chance of an outcome in an experiment, right? Or occurring of an event. right? Probability deals with the predicting the likelihood of the future event, whereas the statistics involved in the analyzing the frequency of the past event with the helps of the data, you understand, right? For example, consider there's a drawer containing 100 socks, 30 red, 20 blue, and 50 black socks. We can use the probability to answer the question about the selection of a random sample of these socks. For example, what is the probability that we draw two blue socks or two red socks from the drawer, right? Similarly, we can frame multiple questions. Whereas, when we talk about the statistics, even we have no knowledge about the types of the socks in the drawer, then we enter into the realm of the statistics, and the statistics to infer properties about the population on the basis of the random samples. That's what we do in the whole of the statistics theory, right? So the question in which can be statistical in nature would look like a random sample of 10 socks from the drawer produces one blue, four red, five black socks. Then what is the total population of these socks or color of these socks, right? So such questions comes in the paradigm of the statistics, whereas answer would come in the probability, right? In the another form, another sense, in probability, we are given the model and asked what kind of data we are likely to see. In statistics, we are doing actually the opposite of this. So we are given the data and asked what kind of model is likely to have generated it, right? Okay, right. Next is the random variable. So a random variable is a rule that assign a numerical value to an outcome of an interest. So for example, if we are tossing a coin, right, tossing two coins simultaneously, and let us define a random variable, say x, as number of heads, right? So if you can write the outcomes, if you toss two coins together, that will be h h, t h, h t, and t t, right? So if we define a random variable the number of heads, it would be, now this random variable x can take values 0, no heads, 1, 1 heads, and 2, 2 heads. Can it take value 3? Can this random variable x we have defined here take value 3? No. Why? Because there is no outcome which is having the three heads, right? And then if we have written the values of the outcomes which a random variable can take along with the probability, right? So what is the probability of getting 0? X means x taking value 0, 1 by 4, right? What is the probability that x taking value 1? 1 by 2. And what is the probability that x value taking 1, sorry, 2, number of hits is 2, that is again 1 by 4, right? Similarly, if we define a random variable x as the number of parents in a married couple who have had childhood list, so this random variable can also take value 0, 1, and 2, right? A random variable is not exactly the same as the variable defining in the data. Rather, the probability that the random variable takes its given value can be computed using the rule governing the probability, right? So we'll see later on. Okay. And next is the probability distribution. So as I said, the combination of a random variable can choose a value along with their probability, what comprises a probability distribution. So when I say that what are the value x can take along with the probability I was giving in the before a couple of minutes, so that if it comprises, that would be a probability distribution, right? So probability distribution is a definition of probabilities of the value of the random variable. So you can see example in front of you on the slides. Given that 0.2 is the probability that a person has had childhood less, then the probability distribution is given by this. Okay. Generally, we, as I said, the value of the random variable along with the corresponding probabilities comprises the probability distribution, and it generally looks like this. Right? In general, a probability distribution function can take the following form, right? And for this particular example, which we have seen in the last slides, we can prepare the probability distribution in this way, or graphical representation of the probability distributions in this way. We have the broadly classified two types of probability distribution. One is the discrete, another one is the continuous one. Under the discrete probability distributions, we have uh, some of the important one is the binomial, multinomial, Poisson, hypergeometric, geometric, etc., and negative binomial as well. The continuous Under the continuous probability distribution, we have the very important one is the uniform, normal, standard normal, gamma, exponential, Wibble, etc. Right? So let us see one by one, and how can we understand these things. Distribution function is widely used in the simulation studies, where we try to generate the same situation like the original one, right? So in this case, we would be using the probability distribution, because it does follow some of the pattern, some of the characteristics of that particular distributions, and therefore when we simulate this, we can get the actual behavior of those distributions to understand any real phenomenon. The use of the simulation studies can often eliminate the need of costly experiment, and it is also often used to study the problems where actual experiment is impossible. You understand, while dealing with the actual thing is very costly as well as not possible sometimes. Rather, dealing with the artificial things is possible. We can repeat it many number of times to get the real idea, real understanding about the actual real phenomenon or the process, right? For example, if a study involving testing the effectiveness of the new drug, the number of cured patients among all the patients who use such a drug approximately follows a binomial distribution, right? So now the meaning of this, that this particular situation have a binomial distribution, and when we say that this particular situation have a binomial distribution, it means it has the characteristics of as same as the binomial distributions, right? So the moment we say that it has binomial distribution, we understood that these situations have the same characteristics as the binomial distributions, right? The important thing is that uh, we denote the probability bar function as a function which gives the probability for the discrete random variable is exactly equal to some of the values, right? And sometimes it's also known as the discrete density function, whereas the probability density function is associated with the continuous random variable to denote the how the probabilities is varying. Now let us see an discrete probability distribution. First is the binomial distribution. Before binomial distribution, we usually talk about the Bernoulli trials, a trial which have only two outcomes in the nature of success or the failure. Such trials are called the Bernoulli trials, right? So it may be treated as yes, no, it may be treated as true, false, it may be treated as 0, 1, right? And then these trials are the Bernoulli trials, and this follows a distribution which is called the Bernoulli distributions. Now, if we repeat this trial to the n number of times, which trials which have only two outcomes as success and failure, to the n number of trials, then its behavior would be called as a binomial distributions, right? So an experiment which consists of the repeated trial, each with dichotomous outcomes, is called Bernoulli process, and each trial is called the Bernoulli trial. And then if we repeat this Bernoulli trial to the number of times, it's behave or it follows the binomial distributions, right? Suppose we have taken a random variable x, which is defined as the number of successes in that trial, right? And such a random variable obeys the binomial probability distribution if the experiment satisfy the following assumptions. So the experiment has to consist of the n trials. Each trial should be mutually exclusive, right, and labeled or understood as a success and failure. The probability of a success, if we denote it as P, should remain constant from trial to trial, and the trials should be independent. Means one trial should be independent of the other. Then, then we can follow or we can get the X successes out of N trials in the same form, right? So that's why the functions for computing the probability related to the binomial probability distribution will be given by this. So that is ncx p to the power x 1 minus p to the power n minus x, where n can take values from 0 to 1, right? So we have seen that it has to be finite number of trials, therefore x varies to n, right? Now let us see the properties of this binomial distribution, right? uh, See this example study. So x is having the probability is 0.2. The probability that a parent has a child in this list will be denoted by p is equal to 0.2. N is 2. Here a couple is an experiment and an individual in trial, and the probability of success is 0. We can put it here as 0. What is probability of 0 successes out of total 2 trials, right? Two successes out of 2 trials, and these probabilities are given here in the table along with the variable x, which can choose the values 0, 1 and 2. Similarly, this is a real life experiment where 10 pairs of random numbers are generated by computer, 15, 38, 68, and so on. If the value of the digit is 0 and 1, the outcome is had childhood measles. Otherwise, digit 2 to 9, the outcome is did not. So, for example, in the first pair, that is 1, 5, representing a couple, and for the couple, x is equal to 1, the frequency distribution for the sample is 0, 1, and 2, right? So, we can, we can have any of the real data, and accordingly we can prepare the distributions, we can fit to the distributions, right? uh, Next is the Poisson distribution, right? Poisson distribution is a distribution which can be approximate from the binomial distribution as well, and we approximate it as, we say, if the number of trials is very very large, means n approaches to infinity, and the probability of success is very very small, that is p approaches to 0, then binomial distribution approximated to the Poisson distribution. So it means whenever we have the number of trials very very high and the probability of success is very small, in this situation we will be using the Poisson distribution, or we will model certain situation with with respect to the Poisson distribution. As far as definition is concerned, so probability distributions of a Poisson random variable x following the Poisson distribution. If it is, its probability given by this e to the power minus lambda t into lambda t to the power x upon factorial x, right? Where lambda is the average number of outcomes per unit time and e is a constant which values is 2.71, right? What is the probability of x is equal to x if t is equal to 0, right? What it could be? Can you tell me? Just do it and tell me afterwards, so that in the meanwhile we'll just finishing the things. The number of customers arriving at a grocery store can be modeled by the Poisson process with intensity lambda is equal to per hour. You can find the probability that there are two customers between 10 to 10:20. You can find the probability that there are three customers between 10 to 10:20 and seven customers between 10 to 10:20 using this Poisson distributions, right? So I'm not going to solve these questions, right? You can note it down and maybe you can solve later on. Okay. Uh, so next is the email distribution. If you would like to calculate the mean of the binomial distribution would be n into p. And if you would like to calculate the variance of the binomial distribution, which is denoted by sigma square, then it would be n p into 1 minus p, which is denoted as q, right? Similarly, in the Poisson distribution is categorized with the lambda, where the lambda is the mean and t is the time interval, right? If you're not using any time interval, then you can remove the t, it will only remain the lambda. So that's one of the good properties of the Poisson distribution, that mean and variance of the distribution both are lambda. So in the Poisson distribution, there is one parameter only which is denoted as lambda, which specify the distributions. Whereas in binomial distribution, we have two parameters n and p, which is required to specify the distributions, right? Uh, Fine. The next is the continuous probability distributions, right? Because in the content we have the other discrete probability distribution, but in the into your curriculum, what we have designed is there is only binomial and Poisson. I'm skipping the another one and coming to the continuous probability distributions. Here you can see that a comparison between the discrete and the continuous, right? So when we talk about the continuous, we do not talk about the probability at the different at specific points, rather than we talk about the probabilities into the interval, and that's how you can see in the graphical representations here. When the random variables of the interest contain any value in an interval, it's called the continuous random interval, right? And every continuous random variable has an infinite uncountable number of possible values in an any given interval. So consequently, the continuous random variables uh, certainly differs from the discrete random variable in this way, right? So you can take any of the examples, the amount of rainfall in in a region, right? This will be a continuous variables. Earthquake intensity is in or on an Richter scales is again a continuous variable. Height of an earth's surface is again a continuous random variables. And when we talk about the properties of this uh, probability density function for a continuous random variables, then it says If we denote by fx, then fx would be greater than or equal to 0 for all x belongs to R. And if we integrate the fx in the complete range of it, then it will give you the value 1, because you know that the total probability is 1, right? Probability of x given a given b can be written as ab fx dx. And if you have to calculate the mean, it again would be given as fx dx. Integrate the x of x with respect to s into the given limits. And similarly, we have the variance, which is again the minus infinity to infinity x minus mu square of x dx here. Now, there are few examples which will make you understand about the continuous probability distributions. Suppose bacteria of a certain species typically live 4 to 6 hours. The probability that a bacterium live exactly 5 hours is equal to 0. A lot of bacteria live for approximately 5 hours, but there is no chance that any bacterium dies in exactly 5 hours, right? This is a example of the probability distribution, right? And we could also understand in this continuous probability distribution that of probability of any exact point will be equal to 0, right? Therefore, in the continuous probability distribution, we always talk about the probability that x is greater than 2, x is greater than 3, x is less than 3, less than 2, rather than x is equal to 2 or x is equal to 3, right? In this case, the probability that the bacterium dies between 5 hours and 5.01 hours is quantifiable, right? Suppose the answer is 0.02, then the probability that bacterium dies between 5 and 5.001 hours should be about 0.002. Since this time interval is 1/10 as long as the previous one, the probability that the bacterium dies between 5 hours and 5.0001 hours should be about 0.002 hours, and so on, right? It means that the ratio is approximately constant and equal to 2 per hour. For example, there is 0.02 probability of dying in an 0.01 hours interval between 5 and 5.01 hours, and 0.02 probability given 0.02 hours will be 2 hours in 2 hours, 2 per hours, right? Therefore, the probability that the bacterium dies at 5 hours can be written as 2 per hour dt. This is the probability that the bacterium dies within an instantial window of the time around 5 hours, where dt is the duration of this time. Clear? The first important continuous distribution is the uniform distribution, right? Which is the simplest continuous distribution and denoted by 1 upon b minus a, where x lies between a and b. And you can see the properties of this continuous uniform distribution. How does it varies, right? Between a and b, it remains same. And all of these are the all of these are the properties of this continuous random variable, which we have seen in case of the general probability density functions, right? Next is the normal distribution. Normal distribution is very, very useful distribution in all aspects, because majority of the things into our day-to-day life, or into in case of the probability distributions, follows the normal distribution for the large value of the n. For the large number of trials, it approximated to the normal distributions, right? And this is also called the bell-shaped curve, because if we draw it for the large number of n, it looks like the bell-shaped curve you can see here, right? This is called the symmetrical about the mean, because the right hand side would exactly be the same as the left hand side. And if you talk about the density of this normal distribution, it is given here in front of you in the slides, 1 upon sigma 2 under root 2 pi e to the power minus x minus mu square upon 2 sigma square, right? Where phi and e is the constants and given their values. These are the properties of the normal distributions, right? And because of their properties, we are very much interested to use these distributions wherever we feel that it's applicable, right? And as I said, that if you see anything in the into your day to day life, or anything which is related to the nature, is always comes in the normal distributions. For example, if you see the heights, right? So if you see the heights of 1000 people, right, and you will find that, and if you plot this curve of those heights of the 100,000 people, then this will certainly will be look like this curve, this symmetrical curve, right, which is a normal. It means that the few people, if we talk about in terms of the height, there are few people whose height will be good, maybe 6 or around 6 feet, and there are few people whose height would be less, maybe around 4 or 4 feet. But the majority of the people will be having a average height which may be around 5, right? That's what the meaning is of having the normal distributions, right? Now these are the three different figures of the normal distributions. All three, and in three, that all two are the, means both of the two figures having the normal distributions, but one is having the mean mu1, another one is having the mean mu2, where sigma 1 and sigma 2 is equal. So what happens? Only this origin shifts from here to here. In this case, mu1 and mu2 is equal, mean is equal, but variance is differ. Sigma 1 and sigma 2 is not equal. And you see that for this sigma 1, this height is certainly peak, and for this sigma 2, this is height is certainly peak, right? Here, both mu1 and mu2 is different, sigma 1 and sigma 2 is also different. You know that when sigma 2 is greater than this sigma 1, obviously this variance, right, variance would be increasing, right? When sigma 1, as sigma 1 is less, the variance would be less. As it would be increasing, the curve would be becoming more flatter and flatter in terms of this rule. One very important empirical rule from this normal distribution, it says that if we have mean mu and a standard deviation sigma, then 68.26% of the data will fall into the limit of mu plus minus sigma. You can see here the graph, right? You can see here the graph. Definitely mu plus minus sigma would be a range. Minus would be this side, plus would be this side. So this range would be comprises this 68.26 percentage. Out of this, 34 and 34 would be divided because it is symmetrical in nature. Again, the 96.46 percentage would be gathered by the range of mu plus minus 2 sigma, right, which is again here given left hand side and the right hand side, right? And 99.73 percentage of the data would be comprising in the limit of mu plus minus 3 sigma, right? That is called the 6 sigma limit as well. 3 of this side and 3 of that side. So 6 sigma limits. And it says that generally everything is lying between the 6 sigma limits, right? I'll give you an example. For example, if you know a class is having an average marks of 50, right, with a standard deviation of 10, with a standard deviation of 10, right? what would be the score of the class in an examination? So you can understand that the majority, or in fact 99.73 percentage of the marks would lies between the limit of mu plus minus 3 sigma. So that is 50 plus minus 30, 3 into 10. So that means 20 to 80. So all the scores of the class would lies between 20 to 80. This is a very advantageous, scope of this probability. Again, we have the Z score. Z score is the transformation. So if you can convert, or if you can choose any such transformation where you can subtract the mean from each value and divide by standard deviation, then it will be treated as Z. And Z is, and this Z score will be follows the normal distribution with mean 0 and variance 1. Right? This is a that is a very very specific generalizations, you may say, right? Because any of such would be going to follow the normal 0 and 1, right? And this is called the standard normal distribution. So if we can subtract, as I said earlier, if x has the normal distribution with mean mu and variance sigma square, then Z will be having the standard normal distribution with mean mu and variance 0 1. This is the probability density function of the standard normal distributions. And how does it look like? You can see here. So a standard normal, if you have to define the standard normal distribution, so the normal distribution with mean 0 and variance 1 would be a standard normal distribution, right? That's all which related to the probability and probability distributions. If you have any questions, you may please raise your hand, or if you feel free to ask any kind of questions. Next is the hypothesis testing. So before we proceed to the introduction of this hypothesis testing, you feel free to ask the questions. No? So I believe there is, okay. Thank you, Elena. Let us just quickly go through the hypothesis testing, and then perhaps we can open the forum for the question and answer. Right. So, in the basic statistical paradigm, we have two approaches. One is the testing of hypothesis, right? And another one is the interval estimation or confidence interval estimation. So, we'll be discussing here the hypothesis testing approach, right? How can we take the decisions? In the hypothesis testing, we have to take the decisions based on the sample, and you can see that's a very beautiful mm, pictures in front of you, that what is the null hypothesis, what is the alternative hypothesis, and what does, how you are going to decide, and then perhaps what is the sample, right? So a hypothesis is nothing but an assertion about the population parameters, right? About a statement about the parameters which is to be tested, right? In 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 very very general terms, we can say that hypothesis testing is a formation of rule under which you have to decide whether to accept or reject the null hypothesis. That's it. And when I say the formation of rule, it means that that rule has to be decided by you, right? You means the researcher, right? The researcher. That is the simple definition of the hypothesis testing, and we always going to do this or follow the same procedures in the hypothesis testing. Now let us see this diagram and their story. A useful analogy for statistical decision making is the decision process used by the jury in a legal proceeding. In a criminal trial, the null hypothesis is that defendant is not guilty, not guilty, right? The alternative is, of course, that the defendant is guilty. The benefit of the doubt goes to the null hypothesis. That is, the evidence must be evaluated by beginning with the assumption that the defendant is not guilty. Clear? The burden of the proof is on the prosecution to demonstrate that the assumption of not guilty is incorrect. That is, the evidence must be gathered to support the claim of a guilty, and the defendant need not to prove innocence. Right? That means you understood with this concept that you always need to prove that someone is guilty. Okay. Now, jurors must only vote for guilty if they are convicted beyond the reasonable doubts that the defendant is guilty. Basically, the decision process for jurors goes something like that. Assume that defendant is not guilty, evaluate the evidence in light of the assumptions. Could all the evidence presented simply by the coincidence? That is, could the degree that evidence points to guilt of the defendant just be explained as coincidence? What is the chance of that? If that chance is small, then vote for guilty. Otherwise, don't vote for guilty. How small is a small chance? Whatever the jurors interpret as beyond the reasonable doubt. Clear? So, in a statistical hypothesis testing, the principle of the trials carries through quite similar. The null hypothesis gets the benefit of the doubt, and the burden of the proof is on the alternative hypothesis. The experimenter must have a test statistic which convince us that the alternative is true rather than the null hypothesis. The same question must be asked as we make a statistical decision as that asked above by the jurors, right? Now let us see with respect to the hypothesis testing. So if the hypothesis is stated in terms of the population parameter, it is called the statistical hypothesis. Now, sample would be used from the population, right, to validate the hypothesis. And the procedure that enables us to agree with the statistical hypothesis is called the test of the hypothesis. So, as I said in the beginning, that it's a formation of the rule under which you have to decide whether to accept or reject the null hypothesis. So, that rule has to be prepared by you, right? Rule has to be prepared by you means you have to prepare the hypothesis, you have to prepare the level of significance, you have to prepare the doubt, right? Or in terms of this discussion, the benefits of doubt, after which you have to allow to the null hypothesis as accepted or rejected, right? There are few examples which can comes under the paradigm of the testing of hypothesis, like to determine whether the wages of the men and women are equal, a product in the market is of a standard quality, etc. uh, the main purpose of the statistical hypothesis the testing to choose between the two competing hypotheses. For example, one hypothesis might claim that wages of a men and women are equal, while the alternative might claim that men makes more than women. Right? Hypothesis testing start by making a set of two statements about the parameters in question, means for which we are trying to decide. Here the wages is the hypothesis actually to be tested is usually given the symbols H naught and commonly referred as null hypothesis, and the another one H1 as alternative hypothesis. The two hypotheses would be exclusive and exhaustive as well, right? You know the meaning of exclusive and exhaustive very well. Let us see an example. Ministry of Human Resource Development, Government of India takes an initiative to improve the country's human resources and hence set up 23 IITs in the country to measure the engineering aptitude of graduates, MHRT graduates examination for a mark of 1000 in every year. A sample of 300 students who get examination in 2020 were collected and the mean is observed as 220. In this context, now so far there was the situation. Now the question begins. In this context, a statistical hypothesis testing is to determine the mean marks of all GATE 2020 examinee, right? And the two hypotheses in the context would be mu is equal to 220 or mu is less than 220, right? That's the two statement which we made in terms of the null hypothesis and the alternative hypothesis, which is to be tested based on the sample, right? How many total students were there? How many samples are there? Okay. So as a null hypothesis, we could choose mu is, we could, as null hypothesis, we could also choose the null mu is, yeah, mu is less than or equal to 220 or mu is greater than or equal to 220. It's customary to always have the null hypothesis with an equal sign and therefore we are choosing with an equal sign. As an alternative hypothesis, there may be the options available that mu, we can choose mu is less than 220, mu can greater than 220 and mu cannot be equal to 220. The two hypotheses should be chosen in such a way that they are exhaustive and exclusive in nature, right? And one or other must be true, but they cannot both be true. So we have to be taken care in such a way. So we have decided this hypothesis. Now there is a concept of one-tail test and a two-tail test, right? A statistical test in which the alternative hypothesis specifies that the population parameters lies entirely above or below of the specified value in the H naught is called a one-sided or one-sided one-tail test. Actually, if you would uh, consider the critical region, then if it the critical region of the test is one-sided, then it will be called as one-sided or one-tailed test. Otherwise, it would be called as two-sided or two-tailed test, right? So obviously, if it is one-sided, means the critical region would be one-sided. Otherwise, it will be only two-sided. There might why I'm using here the critical region only, because there might be a possibility that your alternative hypothesis may not choose the value always both not equal to. So when it is not equal to, then perhaps you tell it is the two-sided test, right? But there might be a possibility that your value cannot be chosen as not equal to. It may only be one-sided, right? So in that case, rather than only seeing the alternative hypothesis, we could also see the critical reasons. Anyways, now what is the procedure of this hypothesis testing, right? So first of all, you have to specify the H naught and H1, right? Null hypothesis and alternative hypothesis, then decide the acceptable level of alpha, determine the appropriate sample-based statistics and rejection region for a specified H naught, collect the sample data, calculate the test statistics, make a decision either for reject or to accept H naught, and then interpret it in the original form of the problem. That's it, right? And you see that in this all procedures, it's all given that you have to decide. And that's why in the beginning I said it is the formation of rule by you, in which you have to decide or in which you have to accept or reject the null hypothesis. Nobody else is going to decide that rule. You have to decide. But the very, very important thing is that you have to decide that rule before starting the process, not in the process or not in the middle of the process, or and you cannot change the rule in between the process, right? Has to be very, very careful. In summary, we have to choose between h naught and h1, and the standard procedures to assume h naught is true, right? Using a statistical test, we try to determine whether there is a sufficient evidence to declare h naught is false. So if we reject h naught only when the chance is small that h naught is true, that means probability is very, very low that the h naught is true, then only we reject the h naught. The procedure is based on probability theory, that is, there is a chance that we can make an error. Now, you know that we have to accept or reject the null hypothesis, and in this case, there can be a two kind of error which can be committed, right? What happens if if h naught is true and you have accepted, there is no error, it is right decision, right? But if h naught is true and you have rejected, this is an error which is called type 1 error. And if h naught is wrong and you have accepted, this is again an error which is called a type 2 error, right? The fourth option is h naught is wrong or false and you have rejected, so there is again no error. So type 1 error and type 2 error, which is rejecting the h naught when it is true, and type 2 is accepting the h naught when it is false, right? And if we take the probability of the type 1 error, right, that is denoted as the alpha, and if we take the probability of the type 2 error, it is denoted as the beta. Alpha and beta are not independent of each other, as one increases another one is decreases. So when the sample size increases, both to decrease since sampling errors is reduced. And in general, we focus on type 1 error, but type 2 error is also important, particularly when the sample size is small. Now, how can we calculate the alpha? Assuming that we have the result of random samples, and then we use the characteristics of the sampling distribution to calculate the probabilities of making the type 1 or type 2 error. Suppose we have the statistical hypothesis that not mu is equal to A, mu is not equal to A, and also assume that for a given sample population obeys normal distribution, and let us see a threshold values A plus minus delta is used to say that they are significantly different from A. Now we can calculate the value of the alpha using these procedure, right? A shaded region implies the probability x bar is less than A minus delta or x bar is greater than A plus delta. So if x bar denotes the sample mean, then the type 1 error is this one, when mu is equal to A, that is when h naught is true, right? In another way, the rejection region comprises the value of the test statistics for which the probability when the null hypothesis is true is less than or equal to the specified value of alpha, and the probability when h1 is true are greater than that they are under h naught, right? So if you can see this diagram, right, you understand when it lies, the value of the test statistics lies in this rejection region, we reject h naught, right? And when it is in the acceptance region, apart from the rejection region, right, then we accept the s naught. Clear? Okay, one tail test and two tail test we have already discussed. If the critical region is of two sided, it's called two tail test. If the critical region is one side, it's called one tail test. Nothing else, right? You can see the picture here as uh, as one tail test and two tail test. It is left, we can say the left tail test. If the critical region is only the right hand side, we can call the right tail test, right? Let us see an example quickly. Consider the two hypotheses. Null hypothesis mu is equal to 8, alternative mu is not is equal to 8. Assume that given a sample of size 16 and in the standard deviation 0.2, the sample follows the normal distributions, right? So suppose the null hypothesis to be rejected if the mean value is less than 7.9 or greater than 8.1, and if x bar is the sample mean, then the probability of type 1 error would be alpha. Probability of x bar this greater than this when mu is equal to 8. When sigma standard deviation is 0.2 and the distribution follows the normal distribution, we know that probability x bar less than 7.9 is equal to probability z is equal to 7.9 upon this, and then probability z is less than or equal to minus 0 minus 2.0 2. Sorry, minus 2.0, which is equal to 0.02, and similarly probability x bar will be greater than 8.1, so this is again 0.0228, right? So hence alpha is equal to, because both hand side, right hand and left hand side, right? So the total alpha will be 0.0456. Clear? Similarly, we can have the another example for calculating the alpha and beta, and we can do this. Let us see this case study. It's a very, very interesting case study which will give you the idea about the hypothesis testing quickly. Suppose a coffee vendor nearby Havra railway station has been having average sales of 500 cup per day. Because of the development of a bus stand nearby, it expects to increase its sales. And during the first 12 days after the inauguration of the bus stand, the daily sales were recorded or sample would be taken, and it is given below 550, 570, and so forth. On the basis of this sample information, can we conclude that the sale of copy have increased, right? And we can consider the 5% level of significance. I hope the question is clear to each one of you, right? Now, with the help of the testing of hypothesis, we need to decide whether the sale of the coffee vendor have already has really increased or not, right? Now let us see here. So these are the few steps which you know very well, right? So first of all, we have to decide the null hypothesis and the alternative hypothesis. So let us consider that the cell or the average is 500 cups per day only. That is the null hypo, that the cell average 500 cup day, and they have not increased, right? Usually we denote the null hypothesis is in the like or in the assumptions that there is no difference, there is no change, something like that. So similarly we have decided that there is no change, it's 500 only. Alternatively, you want to test that whether it is increased. How have we written mu is greater than 500? Why not mu is less than 500? Because in the question it was given to test that the cell has increased or not. So our intention is to check, right, whether the cell is remains same, keeping in mind that it has increased or not. Clear? So acceptance or given level of significance is 0.05, right? Sample is this. In this case, you know the standard deviation is not given, right? And the data is also not 30. So sample size is small and the population standard deviation is not known. Therefore, the t-test can be applied, right? And in case of t-test, the test statistics is x bar minus mu upon s upon root n, and this will be here if we okay, so if we calculate the x bar 548, if we calculate the the different values, that would be s 46.68, and therefore the t values is 3.558, right? So we have the calculated value as 3.558. Now in a statistical table for t distribution, right, the degree of freedom, and for alpha level of significance, we have, since we have the 12 number of observations, so degree of freedom would be n minus 1, that is 11, right? And at this 11, we have the value of the T statistics for 5% level of significance is 1.796. 1.796. And since 1.796 is the rejection region, and you can see that we have calculated T as 3.558, which is in the rejection region. Means the rejection rule is what? If the value of the T is greater than 1.796, let us reject the null hypothesis, right? Let us reject the null hypothesis. And in this case, the null hypothesis is being rejected because the calculated value of the T statistics is greater than the tabulated value of the T statistics, right? The same you can apply into the softwares, and you can also take the decision based on the p value, right? You need not to get the t tabulated and t calculated. It directly gives you the p value in the softwares, and you can take the decision based on that. Okay, so we can conclude here that the sample data indicates that coffee sales have increased, right? So this is what is being taken the decision based on that. So I'll just take you again through on the initial question, and then using the using the testing of hypothesis we have decided. Now these are the different scenarios under which we have to use the z statistic, t statistic, right? This is comprises. So in the case one, normal population infinite, sample size may be large or small, variance of population is known, then we can use the Z test, right? When population normal, finite, sample size may be large or small, and variance is known, we can use this Z statistic. Population is normal, infinite, sample size is small, variance is unknown, we can use T, and we have to approximate sigma with s where s is given, right? When the population is finite, we can use this t, right? That's all from my side. Now you are free to ask the questions related to either the probability or the uh, probability or the testing of hypothesis.
Thank you, dear Professor, for nice presentation. Now, I would like to ask to all the participants, you are allowed to unmute your mic. If you have any question, please feel free to ask. You can unmute your mic to put your question.
Thank you, sir, for excellent explanations, very clear and easy to understand. I have always problems how to link on linguistic. I think here not on the statistic, but on linguistic, how to correctly write the sentence about if the hypothesis is rejected or not. Could you maybe give us some simple example? So how to write this? Thank you very much.
Okay, so Elena, as I could understand, you asked that how to decide whether to accept or reject the hypothesis, right?
Yes, and how to write this in the work. Just
Okay, so
how
how
to
to
say,
write
in
in the
English.
how to
In
write
English.
in the
In
form of
English.
the original problem, right?
Yes, thank you.
Okay. So see, whether to accept or reject the hypothesis would be of two kind of procedures. One is using the critical region values, and another one using the p values, right? So when you are using any of the softwares, I had some of the hands-on, but times not permit us to go there. So when you use the softwares, you can directly get the p values. So if p values is less than alpha, whatever alpha you decide, usually is 0.05. So if p values is less than 0.05, you have to reject the null hypothesis, right? And when you say you have to reject the null hypothesis, it means in the original level of the problem, right? Whatever problem we were discussing initially, for example, in this case, the sales of the coffee vendor, right? So we wanted to test whether the sale of the coffee vendor have been increased or not. Why? Because there is a new bus terminal gets open. And then we have taken the sample to decide whether the sales have been increased or not. So ultimately, we have prepared the null hypothesis and alternative hypothesis, prepared the value of alpha, and prepared the test statistics. And based on this test statistics, because the calculation of value of the test statistics was greater than the tabulated value. Tabulated value are given in all the books of the statistics. If you can find the t distribution, so all values are given. Even if not, then you can get it from internet. There is no issue. So if the tabulated value is greater than, sorry, if the calculated value is greater than the tabulated value, then you have to reject the null hypothesis. Now, rejecting the null hypothesis means, in this case of the coughing vendor, we have written mu is equal to 500. It means this is not accepted. And the alternative was mu is greater than 500. So then we have to go with the mu is greater than 500. It means the sales of the coughing vendor has been increased, right? Earlier it was on average 500. Now sale have been increased. That's what we have concluded. I hope I could respond to your question.
Thank you very much. Now I understand.
Okay. Thank you, Alina.
Any more any more question, please?
Good evening, Professor. I'm Dr. B. Basumalik. I have a small question. Am I audible?
Yeah, very much.
Yeah, actually, I just want to know that, while testing the hypothesis, at times we are taking 5% level of significance. At times we also take 1% level of significance. Does that make any difference in the inference of the? I mean,
It is. Yeah, I
so
could understand. It's you as a researcher who have to decide, right? For example,
okay,
if you are preparing a medicine, right? How much error would you like to commit, or how much errors is acceptable? Perhaps not even a 1%.
yeah, sure,
Yeah. But if you are, let's suppose, preparing a door, right? Door of any apartments, right? So then
okay,
you have to prepare 5,000 doors, and there is a specific size of the doors, right? Now,
okay,
how much error in the size of the doors you can accept? You can accept easily the 5%, right?
right,
So it depends on the what you are dealing with and how much you are
right,
allowing yourself to deal with it. Because if you will, keep your alpha as low as possible, then you have
yeah,
to take the large samples, right? And for taking the
okay.
large sample, definitely you have to spend more time, more manpower, more cost,
Right, right,
etc.,
absolutely.
etc.
Yeah. So it depends on what I am dealing with and what is the size of the sample. So
What is
for
the
large
size of the
sample,
sample? What
normally
you
we
are
go for
dealing with?
1% level of significance. But
For the large sample, we can go with it, and definitely the nature, the behavior of the behavior of the situation or the characteristics of the things which you are dealing with.
but if we make a comparative analysis with the same thing, I mean, I have seen that I'm getting two different results. Okay, because generally the value of alpha should be small, because in order to make the type 1 and error 2 small. So why this two different inferences at times happens in a situation if we consider the comparative analysis? So will that not lead to some wrong inference? I'm just asking that. I mean, is it
Uh,
uh,
okay, I could understand. Means you are asking that if we take the alpha as 10%, 5%, on 1%, then the
yes,
results would be different, right?
yes, that's right, sir.
Definitely the result would be increased. If you are able to take the 5% or the error, and if you are
Yes.
error, to take the 10% of the error, right? And if
Yes.
it would be there somewhere 7%, then in one cases you will accept the hypothesis, in another case you will reject the hypothesis,
Yes.
right?
Yes. That's right.
So definitely your result will be different, right? So that
Okay.
threshold value has to be decided by you, and that's why I said in the beginning it's a formation of rule by you. So you have to decide this threshold value in the beginning, right?
Right.
Before
Okay.
starting the procedure, that I am only getting the 5% level of significance, right?
Right.
And this
Right.
this 5% level of significance is also comes from the past data, from the past experiences, and and definitely what kind of what kind of variables or things
Samples.
you are dealing
Yeah.
with.
Right. Right. Okay, sir. Thank you so much. Thank you so much.
Thank
Thank
you,
you.
thank you.
Thank you.
Any more question, please?
Yeah, please feel free. Definitely I am
Yeah.
also learning from your questions, so please feel free, or if you would like to add something here, then also you're welcome.
Dear participant, we are waiting for some more question from your side. Please feel free to unmute your mic and put your question. Sir, can you please suggest some books for the participant for biostatics?
uh yeah, definitely, just give me a moment. uh I will share the, if I see if I have the soft copy of that book, I'll just share it uh by now only. uh just give me a moment. There is one book I remember, that's Biostatistics, a foundation of analysis in the health sciences, by Daniel and Cross. By Daniel and Cross. I had the soft copy. I'll see if I could share with you later on. And the another book is Introductory Biostatistics by, if I'm not wrong, by Chapit Lee, right? So, Dr. Mer, I'll share these two books with you
Okay,
over
sir.
the email,
And
and so that
also,
you can.
please provide us your presentation. This is really very
Sure, sure,
informative and
sure.
knowledgeable, and participant will ask from me, please share the content.
Sure.
Yeah.
All that.
So all these
I'll
content
share
will
that
be
book.
very helpful to all the entire participant who are attending this session. And I always ask to the participant, please feel free to ask any question. Don't hesitate, please.
There is one book which I am sharing now with the participants here only. So that's a very good book by Wiley, and gives you the great understandings of the biostatistics field. Still, if you have any questions, please feel free. I am also here to learn from you.
One book has been shared in the chat box. You can download from directly from that place. And also we will share with you through your email address also all the content which we are printing in WhatsApp group as well as on your email address. And as you know, recordings will be available on the YouTube, and all these link will be shared with you. And regularly we are sharing each everything with you.
I have also prepared a few PPTs related to the hands-on what have we done. So I'll share with you. You can share with the participants, and if you have any doubt, it's very quite simple on the R. But if you have any doubt, you may please email me or text me so that we can respond over you so that you will be able to understand those things.
Sir, I have also one common question from the participant side.
Please, please.
Some of the participants are not familiar with the statistics, but they want to use uh, software like R or Python.
Mhm.
But on the same time, it is very difficult to understand every concept for the participant statistical background. But because there are many methods, but they are not able to memorize all these methods. But these methods are very applicable in their findings if they want. But sometimes without familiarity or understanding the methods, they are not able to hands-on to use in their findings. So can you please suggest when the researcher is using computing tool, how much important these methods to understand or to do manually? So there is some little bit confusion because when there is a software and the software will do everything by giving the command and they can do easily. But on the other side, these methods are also very important as I am also mathematician, and if we have better understanding about this method, then how they can balance with these two?
See, the problem is what happens, the no software is going to interpret, right?
Yeah.
The software can only give you the value that, let's suppose p value is 0.05, f value is 0.16.3, t value is 16.3, your r square is 0.97, right? So no software will tell you what is to be done, right? This is your understanding of the concept who will let you know that what is to be done. For example, I'll say that it might not be related with this presentation, but if you talk about the Cronbach alpha, right? So we calculate the Cronbach alpha for the testing the reliability, and Cronbach alpha will be in the different fields will behave differently, right? Like in the social sciences, the Cronbach alpha 0.7, 0.8 or 0.7, 0.2 something will be treated as very good, right? But may not be in the other field, right? May not be in the, let's say, in the medical field. It has to be zero point 0.9 or more than 0.9, right? But who tells you this? No software is going to tell you that for this particular field, Cronbach alpha is quite justified, and you can go ahead, you can go ahead with your questionnaire, you can go ahead with your things, right? But this is your understanding of the knowledge, right? What actually you are measuring through the Cronbach alpha will tell you, and then you can write in the research papers, maybe your thesis, maybe research papers, and you can justify that even the Cronbach alpha zero point 0.7 is better than the Cronbach alpha zero point 0.9 into the different fields or comparative to different fields, right? That is the important of the understanding. Now, obviously, now we have the multiple tools, and majority of the researchers goes to any person and asks, sir, t test laga dijiye, then you can please arrange some chi-square test, f test, and they give you the value and then write, right? So understanding is very, very important, right? Using the software nowadays is a secondary thing, right? Somebody can help you out. You all know that we have the chat GPT, right? And we can write the codes of the R using the chat GPT, right? So nowadays writing the codes is not a challenge, rather than if you have written the code and code is being executed, now how are you going to interpret the things which is in front of you? That is the challenge, right? And that perhaps required the understanding of the concept that not even the chat GPT can tell you,
Thank you, sir,
right?
for explanation. And Elena, you raise hand if you have question.
Thank you. You have very similar question to mine. So I have got the answer. Thank you.
Thank you.
Yes, yes.
Dear participant, thank you very much to attend this entire session. And thank you, dear professor. I hope this session is really very informative, knowledgeable, and helpful to all the participants in the coming session. Because without these basic concepts, we are not able to understand and how we can implement these methods for our finding to analysis for not only biostat but the other branches also, because the stat is similar but application in all the do- domain. So thank you very much, dear professor, for your valuable time. I extend my heartfelt thanks to you for delivering an insightful session on probability fundamentals for biostatics during our 10 days workshop on biostatics from basic to advanced techniques. Your expertise and the clear explanation have greatly enriched the learning experience of our participant. We truly appreciate your time and efforts in sharing such valuable knowledge. Your contribution has made a significant impact on the success of this workshop. Once again, thank you very much. And tomorrow, dear participant, we will start the session at the same time. And our professor Prayas Sharma have one more session, and that will be based on using R programming. And I hope that that will be very, very wonderful and sportive session for all the participant. So once again, thank you, and we will wait for the next session. Dr. Priya Sharma ji. Yeah,
Thank you, thank you,
thank you.
Dr. Chan, for
And
indeed the pleasure is all mine. And I would also like to thanks to the participants from the patient hearing and 9 question, especially the Elena. Throughout she was responding on the chat. I could see, and then the actively participate in the session. Thank you, everyone.
thank you, sir. Thank you to all, and good night from India.
Thank you, thank you.
Now
Good night.
it is time to end the session.